Great to see you here. This is a new video offered to you by the Ceuster Academy. My name is Luc de Ceuster and I'm the founder of the Ceuster Academy. If you're here for the first time or you did not subscribe to our channel yet, this is the moment to do it. Click the subscribe button, click the bell button, so whenever we have a new video, YouTube will send you a message. What I'm going to talk about in this presentation, in this video, is about prime numbers and trial division. Now, prime numbers are very important in discrete mathematics, in computer science, because we are going to use large prime numbers, for example, in encryption. Working with prime numbers is very important, so it's very important that you understand what prime numbers are and what properties we can use. Let's have a look at the definition. What is a prime number? A prime number is a number which has two divisors, 1 and itself. Now, many times I ask people what are the prime numbers, what is the first prime number? And many people say it's the number 1. But let's have a look. The number 1. What are the divisors of 1? Well, 1 itself, 1 and 1. But what do we see? Those are the same numbers. So basically there is only one divisor. And in order to have a prime number, we have to have two divisors. So 1 is not a prime number. And the first prime number is the number 2, which has two divisors, 1 and 2. Then we have 3, 1 and 3, 5 with 1 and 5, 7, 1 and 7. So these are a series of the prime numbers. Of course, there are infinite prime numbers. And when we look at the list of prime numbers, we can have a look at some prime numbers. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and then we have 31, 37, and so on. You can find a lot of applications or papers where you find the prime numbers. You find them on the internet, you can make a list, it's not a problem. You find them everywhere, and you can also find a way to identify a prime number. Now, when a number is not a prime number, we call them a composed number. A composed number is a number that is composed of a product of prime numbers. And when we look at a product of prime numbers, for example, the number 2310 is a composed number. Why is that? Well, when we start dividing, and we're already starting with the trial division, we start dividing by the first prime number. So we divide by 2. And when we divide by 2, we find, in fact, 1155. We see, or we can find here, we try to divide again by 2, it doesn't work, because in a composed number we can have more prime numbers. For example, we can have 2 to the power 6. So 6 times 2 is a possibility. Now here we can see, we try with the next number, which is 3. And when we find the division here, we find that it's 385. And a number ending on 5 is 5, divisible by 5. So I find here the number 77. Yeah, and 77 is quite easy. Yeah, 7 we find, which is the next prime number, and we find 11. So basically we can write the number 2310 as being 2 times 3 times 5 times 7 times 11. And you can do that for any composed number. Now, what do we want to do when we have a number? Whatever number we have, and we want to find is it a prime number? We're going to apply the principle of trial division. And that's what we're going to do with a number, let's say 379. So we start with the number 379, and we start by dividing by the first prime number. We find the number is 189.5, so it's not divisible by 2, and we continue this number like that. So we're continuing that division. We already see it's not divisible by 2, so we take the second prime number, so 379 divided by 3, which is equal to 126.333, and so on. Also not divisible. Now we take the next one, 379 divided by 5. Well, we can immediately see that this is not divisible, and when we calculate it is 75.8. And we continue, so we have now 379 divided by 7. So basically what we find here is 34.5. We take 379 divided by 11, the next prime number, and we find here, oops, I forgot this one, but we will see that it's not divisible. Then we have 379 divided by 13, which gives me 29.1. And then we continue, 379 divided by 17, which is equal to 22.3. And 379 divided by 19 is 19.9. And the last one that I will use, 379 divided by 23 is 16.5. Now what we see here, the prime numbers increase, and the result of the division decreases. Now what do we see here? We have a certain moment here when we have 19, we divide by 19, and we find it's 19.9. So what does this mean? Well, it means that we have a kind of symmetry when we look at the numbers. We have numbers at both sides of the 19.9, and basically when we are going to divide by higher prime numbers, the result will be lower. But we already had those lower numbers. When we are looking into an algorithm to find a way how to calculate this, and we've seen it in some theoretical approach, when we look at the square root of the number, is in fact, in this case, the square root of 379 is 19.4, which is basically the symmetrical point. So whenever we arrive here at 19 and we didn't find a prime number that divides 379, that means that 379 has not a prime divisor, and it means in this case that the number is prime, it's not a composed number. Let's continue with some more properties about the trial division. Let's take any number. Any number n can be written as a product of two integers, positive integers, and it leads to a pair a and b for which a times b equal to n. Now we have different cases. Let's say a is equal to b. It means that n is equal to a to the square, or a to the square is equal to n, or b to the square, it's the same. And we can say that a is square root of n. Another element that we have, when a is smaller than b, and a times b is equal to n, it means that a, in this case, is smaller than square root of n, and b is larger than square root of n. And when a is larger than b, we still have ab equal to n. We find that a is larger than square root of n and b smaller than square root of n. Now what we have to do is that we have to do the trial division until we reach square root of n. Or even better, since we're dealing with basically natural numbers, the positive integers, we have to go until we reach the floor of square root of n. So this means basically that when we're doing the trial division, when we're writing an algorithm to do this, we don't have to go through all the numbers n, we only have to go to the square root of n, which has an effect on what we call the time complexity of an algorithm. We talk about that later when we're talking about algorithms. Let's take a number. Let's take an example, square root of 18, or n is 18, So n is equal to 18. So the square root of 18 is 4.2. That means that the floor of square root of 18 is in fact 4. So we only have to go to the fourth number, to 4, to find the possibility. Now what do we have here? Now let's look at those different pairs that I spoke about. So when we look at 18, what are the pairs that I can find? First pair is 1 and 18. So the product of those two is in fact the value of 18. A is smaller than b, and then b is larger than square root of n. So we have a equal to 1 and b equal to 18. The next one we have 2 and 9. 2 times 9 is also 18, so we find a is equal to 2 and b is equal to 9. And the last one that we can find is 3 and 6, and we find a is 3, b is 6. Now what happens here? I can continue the numbers here. A can increase, and I can find here 6 and 3. But basically what happens is that we find a symmetry here. So we don't have to continue further. Now basically this means that big O of this algorithm is square root of n. So we could go through all the numbers, which would give us n. We could go through half of the numbers, which would be n over 2, but square root of n is a better time complexity. Time complexity means less calculations and less computer time. But that's the first thing. Now the next problem that we want to know is, I want to find all the prime numbers between 2, the first prime number, and a specific number, let's say 50 or any other number. Now what I have to do, I have to look at all those numbers, and there I will find from 2 till n, all the numbers there. I will find that the time complexity, I have to do this n times, because for every number I have to calculate, is this a prime number, yes or no? So when we do that, we find a time complexity n times square root of n. But in the next part you will see that we can improve this thanks to a very old algorithm. Within the study and the identification of prime numbers, we have also a very interesting way to find all the prime numbers between 2 and any integer. We call it the Sieve of Eratosthenes. Here we're going to find what are the prime numbers between 2 and 26. Now remember that we spoke before about square root of n, and n in this case is 26, which is about 5.1. Now when we take the floor of the square root of 26, we see that this is equal to 5, and we will see that that number comes back. Basically by looking at this, looking at those values at the number 5 here, the square root of 26, we will see how small, we will basically see that we can reduce our calculations, and like we have shown before, another important thing when we look at prime numbers is that we want to know, for example, all the prime numbers between 2 and a specific integer, in our case 26. And to find those numbers, we're going to use an old algorithm, which is also called the Sieve of Eratosthenes. Now we spoke about n before, n in the previous video, or just before this part of the video, is 26, and we calculated the square root of n, which is approximately 5.1. Now when we take the floor of the square root of 26, which gives us 5, and that was in fact related to the complexity to find if a number is a prime number, yes or no. So what we can do is to do or use the classical algorithm, find all the prime numbers for n, so we find all those numbers for every number. This is about 5 calculations that we have to do, but we have to do that for all of the numbers. So basically, in the classical approach, we would find a time value of n, square root of n. So that's the number of calculations. So for every number n, we have to do square root of n calculations to find if the number is prime or not. The Sieve of Eratosthenes will help us to do this a lot faster, and we will see that it works very efficiently. What we do, we take the first prime number, which is 2, and we eliminate all the multiples of 2 in the sieve. So we put them in a framework here, and now we are going to eliminate all the multiples of 2. So 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. So that's basically the first thing that we do. Now we do the same thing for the second prime number. So P2 is equal to 3, and we eliminate all the multiples. 6 has already been eliminated because it's a multiple of 2. 9 is a new one, 12 was already eliminated, 15 is a new one, 18 was already eliminated, 21 and 24. So basically we already eliminated a large number of numbers which are not prime. And we already see 5, 7, 11, 13, 17, 19, 23, those are already prime numbers. We still have some other numbers, so we still have to do this for 5. Now we are doing this for 5. The third prime number is 5. We eliminate, or we take 5 and we eliminate its multiples. 10 we already had, then we have 15, then we have 20, and then we have 25. And what do we see at this moment? We don't have any more numbers left which are not prime. So basically the prime numbers are 7, 10, 13, 17, 19, and 23. Now, with more mathematics, when we look at algorithms, we can prove that the time value, the time constant, is n log n, which is in fact a lot less than the classical approach that we had before. So basically we looked at the prime numbers, how to find if a number is a prime number by trial divisions. We looked at the size, we looked at improvements of that algorithm, and basically the last thing we did was to introduce to you the old algorithm, the Sieve of Eratosthenes, to show you how we can find all those prime numbers between 2 and any integer value. So that was it for this video. Don't forget to have a look down in the description, because you find very interesting links to our courses, coupons that will give you a very nice discount. And of course, like at the end of every video, please do not forget to subscribe if you didn't do it yet. Click the bell button so every time we have a new video, YouTube will inform you. I thank you very much, and I'm looking forward to seeing you in our next video. Thank you and bye-bye.